Hello, welcome to this lesson in calculus limits. I'm excited to teach this lesson because it's the first time in this whole set of lessons where I can really give you at least a little bit of an idea of why limits are useful. You know, limit theory leads into the concept of a derivative, which we're going to study much later in my other calculus sequence that I already have. And derivatives apply to everything in science and engineering. And derivatives are really defined in terms of limit theory, and so to really understand how they work, you have to understand limits. All right, so in order to kind of get the show on the road a little bit, just kind of keep in mind everything that we've done before and find the limits of the functions that we've done and the idea of approaching and seeing what the limit is. Now let me ask you a question, because we're going to talk a little bit about position and velocity. If I ask you how to count, if I tell you something's moving, like if a bowling ball is moving across the room and it's going across the room at some speed, I don't know what the speed is, but I can measure that the ball was here at one point in time, and then 2 or 3 seconds later it's over there, 2 or 3 seconds later it's even farther, okay? If I want to figure out what the average velocity is of that bowling ball rolling across the room, how do you do it? Well, you all know that velocity is meters per second or miles per hour, or kilometers per hour, kilometers per minute. Anyway, it's always a distance over a time. So if you want to find out how fast something is moving over a time period, then what you do is you measure how far it moves in meters or whatever, and then you figure out how long it took for that to happen in seconds, and you divide meters per second. That's what velocity is. But keep in mind, when you do that, you're really getting the average velocity, because for a bowling ball, it's pretty much going at the same speed, right? But when you have something like a rocket, maybe accelerating, then the speed is always changing. But anytime you take two endpoints, like a starting point and an ending point, and you look at how far it moved and how long it took, and you divide those, you're getting the average velocity between those 2 points. But as I said, we're in calculus now. We're not in basic, fourth grade anymore. So we don't want to know what the average velocity is of something that's moving. We want to know what the velocity is at a certain point in time. So if you take a more complicated problem, such as, for instance, a rocket ship or something, like a rocket going into space, then you might say that this axis is t in seconds. Okay? And you might say that this is f of t, some function of time, and you might say it's meters. So what this plot is really showing is how high the rocket goes versus time. Okay? So because rocket's really fat and heavy at first, it's not moving so fast, but as it goes higher and higher, it gets lighter and lighter and lighter, and it starts basically going up a curved path like this. Now this is not representing the launch trajectory. This is basically saying that as time goes along, the speed, the distance the rocket has traveled is actually covering more distance, is another way to look at it. Like between this point in time and this point in time, it only moved up a teeny bit. But between this point in time and this point in time, it moved up even more. And between this point in time and this point in time, and this point in time and this point in time, it moved up a whole lot. So you can see that in this particular graph, the speed of this rocket is not constant. The velocity is not constant. It's actually increasing because the thing is zooming up like that. Now, if you had a bowling ball or a car or something like that that was going at a constant speed or velocity, then it would look something like this. If this is t and if this is, f of t, the position function, then it would look something like this. It would be a straight line if it was constant speed. Because see, for constant speed, for every second that you go along, every 2 places you put your fingers and you look at increments of 1 second, the thing has moved the same distance in the direction of travel because it's a constant slope. So everywhere you move, the thing